All right, the first thing I want to talk through is a review of the basic forms from Calculus 1. All of you, if you've been through a good Calculus 1 course, should have learned all these basic forms. If you go on my webpage and where it says basic forms are here, you can get a hard copy of those. You will want probably to get I would guess you'd want to get a hard copy of those so that you have access to those easily as you're working through your work if you need them. But these need to be in your mind. You need to know these as well as you know that 2x plus 3x is 5x. As well as you know that, you need to know that the derivative with respect to x of tangent of u is secant squared of u times u prime. Now, all of these derivative forms, and see, that would be from numbers 1 through 18. All of these derivative forms are given with the chain rule structure, so that it's the derivative with respect to x of tangent of u, where u might be a larger expression. And so in a particular case of this might be d by dx of tangent, and the reason this is written as u is because it could be a larger function. It could be, let's say, 3x to the second. So in this case, the part of u is being played by 3x to the second. And so when this structure with the u and the u prime, this emphasizes the fact that you need to use the chain rule, which is to say the derivative of tangent of something is secant squared of the something, and then you must multiply, chain rule, by the derivative of the argument of this secant squared function. And so that's 6x. And so that's the derivative. It's using secant squared of u times the derivative of u. The point, okay, so that's the structure of this. But the point is, all of these are Calculus 1 material. You should have learned all of these in Calculus 1, all the way down through the derivatives of the inverse tangent functions. The only inverse tangent functions I will deal with typically are sine inverse, tangent inverse, and secant inverse. There's anything that can be done for our main thrust. Anything that can be done with cosine inverse can also be done with sine inverse, and sine inverse is easier. So we'll go ahead and use that. Now, the integral forms are also in terms of u. So these are in the u forms, and so you would need to know that the antiderivative of secant u, tangent of u, du. What's the antiderivative of secant tangent? We know that is secant. And how do we know this? Because the derivative of secant is secant tangent. Therefore, the fundamental theorem says the antiderivative, or not fundamental theorem, but the antiderivative then of secant secant tangent is secant. Each of these has the constant on because these are indefinite integrals. A couple of these might just be to note. Number 24 and number 25 are two different forms of the same rule. Number 24 says it's the antiderivative of 1 over u, and number 25 is the antiderivative of u to the negative 1. The reason I list both of these is because they both arise. Certain problems lend themselves to generating this form. Other problems lend themselves to generating this form, and it's just convenient to be able to use both of these. Sometimes students learn only this, and then whenever this arises, they go to the extra step of translating, finding the result, and then translating back, or vice versa. Anyway, I have both of these listed as basic forms. In either case, this is the natural log form. And remember, it's natural log absolute. And so both of them have the same result because they're the same problem. It's just the format, it looks different, but it's really the same notion. One small detail. What if we had out of this received natural log of something like, let's say, absolute x squared plus 3. Let's pretend this had been our final result. If you check your answer with a textbook or with online or Wolfram Algebra or something like that, if you check your answer, the text might not write this. The text will write this. And sometimes students get confused. They say, I thought you had to have the absolute value. Well, you do need to have the absolute value. However, if the quantity in question must be positive or cannot be negative, if this quantity in question is never negative, if something is not negative, the absolute value of that quantity is the quantity. And so if this quantity can never be negative, the text will never write this with absolute value. It will actually simplify the result and not use the absolute value. Is it clear that if you take a number and square it, it's positive, and then if you add 3, it's still positive? So this number can never be negative, or it's never, x squared is non-negative and add 3 is always positive. If this happens, I don't care if you write this form, I don't care if you write this form. The only reason I mention this is if you want to check with your answer with the textbook, you will need to recognize that's what's actually happening. This happens over and over and over again. And so if this occurs, you just need to be aware of that. Anytime you have the absolute value of something that cannot be negative, the textbook will omit the absolute value bars. Other than that, I think all the basic forms are straightforward. And those should be well within your experience. If they are not, get a copy of them, study them, learn them. They need to become part of your mental furniture so that you can work through these without hesitation. As soon as you see the integral of cosine, you know it's sine. If you want the integral of sine, you need to know immediately this negative cosine and go from there. So, basic forms, make sure you learn them. You'll hear me hammering on the basic forms throughout the entire semester. So, there we are, and make sure you learn your basic forms.